Okay. So yeah, there's a way that I need to follow this. So this is I'm going to solve the spring 2018 exam 3 problems and the nuclear chemistry. And you start from something from here, number 10, and I solved this one from the previous one. So you guys can see that the answer keys from the YouTube session, YouTube videos that you can see that. Okay. It's just actually very simple. For example, if I go back a little bit, polonium 20, number 12, 214. So polonium, you have to look for your periodic table and look for the symbol PO. And sometimes it's not easy to find out, but if you look at the PO right there, and you look for the number 84. So nobody remember polonium is 84. It's not the point. So it's just 84. You can find out from the periodic table, and anywhere is available. But there's a 214 means that's the number of protons and the neutrons. Okay, and then transmuted, which is transformed to lead. Lead, you need to know the symbol lead, which is a Pb. And if you look at the Pb in the periodic table once more, it's right there. Pb is the number 82. So then you write 82, and then to 210. And then you finish up this arithmetic saying 84 minus 82 must be 2, 214, 210 is 4. That's a helium. And then you look for the, helium particle emission. And unfortunately, they don't say that. They just say, then we call alpha particle for historical reasons. So then you can say alpha emission from the reactor nucleus. Okay, so that's what I say. Anyway, number 13 is a key point that I'm going to start today. And then this is actually, it pays off just what I talked about, how the half-life the means in a more meaningful way. So let's say this ytterbium. Ytterbium is actually has a symbol of Yb, and the beta emitter of a half-life of 101 hours. So you can write half-life 101 hour. Okay, so that's good. And then how long would it take for an activity in a sample isotope decay to exact to the 1/5 of its original value? Okay, so it is a question that 1/5 of original value, dk2, right? So this one now, if you write this, I think this means what it means is that they want to know concentration A become 1/5 of original concentration, right? And then you also know, for example, A over A naught is minus KT. So now you know, using this notation, you can plug that in, A value, and then that will naturally give you to this value about natural log 1/5 is minus KT. So they want to know what's the value of T. So this is how long is, which means a T, right? How long, what is the time? And the answer is right there. And then the only thing that left is you need to know your K value. So what did we say about this before? Half-life is natural log 2 divided by K. So therefore K is ln 2 divided by half-life, which is a 101 hour. So by doing so, it's actually hour goes in the bottom, so the unit of K is actually inverse hour, and you're going to plug that in right there, and then this one becomes ln 5. So everything here you put it in, ln 5 equal K is 101 ln 2 times T, and T must has a unit of 1 hour. Okay, And then if you put that all that in, and you will get this answer of 235. So that will be a very meaningful. Okay, the second problem is actually related to my crash course number 1 version, and this is actually quite important, and it's good to know. I refresh my memory about this. What is called the value of stability? Okay, if you guys remember the value of stability in the lectures, I can only type because my camera mic doesn't work. Yeah. Okay. Okay. So you guys can can you guys hear me, right? So you guys can type any questions in the chat box. You guys can see my hand, right? Say yes. Yes. Okay. All right. So let me go talk about what do you mean by value of stability. I hope you guys remember that. So let me draw this my graph. So this is a y-axis. This is an x-axis. And what I'm showing here is starting from 0. And this is what they call the z. Okay? And this is what they call n. And z is an atomic number, which is the same number as the number of protons. So, I can put a little number as a parenthesis as a p. This is same number as a neutrons, right? Okay. And then what I have is I am going to put a dotted line. This is a line called n over z is 1, which means the same number of protons and same number of neutrons are the same. And that's and then they look at essentially all the different atoms, and then they actually, you probably, if I draw this one now, you probably not start to remember. They start to, let me get rid of this. Okay. Yeah, like this one. They start to notice that there's a certain tendency what is common in nature. So this is what you see, the orange shaded area, that is a value of stability. That's where all the atoms are more like to be located. Okay, so it has a meaning, and then I think they even probably in the lecture say, okay, up to 0 to 20 for z, for the value of the z, and you'll find out n over z is 1. Okay, same number of that. And if you go up, it's like 20 to something like, I don't know, 40, and that number is 1.25 and so on. That's what they talked about. But I think that here I'm going to put a red colors and put an emphasis on here, and let's read this problem carefully. Okay, nucleotide above the value of stability. Okay. Well, what that means is there's a nucleotide locate themselves right here. You see the red dots? And that's the one they are above the nuclear value of stability. So this yellow one is this is a valley, right? The value of stability. And then your nuclei located themselves. So what that means is you are happy in this orange region, and if you're outside of it, you are not happy. So what this nuclei are trying to do is, I want to either go this way, or I want to go down this way, to be in the happier state. Okay, so this is the one you are unhappy. Okay, you're unhappy, but you will be happy within the value of stability. Okay, this is where you want it to be. This is your happy place. So what's happening if you're moving from the left to right? You are going to essentially increase the number of protons, right? So that's the one. So that's actually the answer can be found from here. Let me do the undo. Okay. So let's get rid of this. So this one is just a background. So I need something. So what happened here is this nuclei X must have a number Z, right? And then, I don't know, N plus P, if you want to call it. So that's the one. And if they want to lose and then increase the number of the protons, And what do? They have to be like this. If they do this, and the z number goes plus 1, right? And n plus p. And that will be, okay, it's a y, right? That's a different atoms. But you are closer to the value of stability because you are here and your proton number goes up by following this path that I just highlighted here, right? So this, what happened here is by this beta emission, A will be the answer, okay? And so let me choose another problem that is I wanted to discuss with you one more time here. What about here? If you are here, if you are nucleotide below the value of stability, then what do you want to do? You want to actually decrease the number of protons, right? And in that case, this one is, I would say, x z n plus p. They want to actually -1 to e. They want to do the reaction so that their number is decreasing. Number of protons are changing from z to z minus 1, n plus p without y, right? So this is a case for this particular reaction. This one is a nucleide below the valley, right? And then what do you call this reaction? That's an electron capture, right? So you can see that the electron capture will be answer for the case of the B, okay? The below the value of stability, okay? So I think that these types of graph was discussed, and you can look back your lecture note, and you can find out what that means. Number 15 is not so difficult, and it's just bookkeeping in a way. So let me give you an idea. Okay, so the rhodium, and what's a rhodium? So the job that you have to do is you have to look for your periodic table and where the rhodiums are. Okay, and the rhodium is where are you? Yeah, 45. Okay, so you see the rhodium, 45. So the important one is if you write this rhodium 45 103, you are like halfway done to solving this problem. And from here, what you see is this is your rhodium nuclei. There are neutrons and the protons, and you just figure that out, how many protons and how many neutrons are, right? And then and this one itself has a neutron is actually, let me start with the proton 45, and then how many of the neutrons? So you have to subtract that 103 by 45. That's a 58. Okay, 58 neutrons. And then the 45, the proton has a mass of this, right? So proton has a mass of 10072764669, and the neutron, it says this 1.0086649,156. So as an individual particles, this is the way that the weight that's supposed to happen, and if you just add it up, and then this is if you have essentially 45 times P plus 58 times N, which is same number of protons and neutrons as a rhodium atom, the nuclei, you will get the number that is 103.83.000.61153. But what this problem is telling me is this rhodium as it is, okay, what I highlighted is this one, right, has this mass. Right? So then what you do is, okay, I can subtract this number, which is just a collection versus rhodium, and which is the mass is 102.9055. Okay, so if you subtract that, and that's the mass differences. And the mass difference is 0.9245 AMU. Okay, so this is the mass and the energy equivalence. That's what is one of the famous equation by Einstein. And where do I find the energy conversion? You don't have to remember. You just go back to your notations that the information was given to you. If you look at that, 1 AMU is 931.5 mega electron volts. And even further, 1 electron volt is so many joules, right? So you can actually, AMU can be converted into the electron volt. That electron volt can be converted into the joule. So let's just do that, okay? So therefore, the energy is 0.9245 AMU, and you remember unit conversion, right? AMU, mega means 10 to the 6 electron volts, so I will do the electron volts, mega electron volts right there, but it's 931.5 mega electron volts is 1 AMU, okay? And by doing so, AMU is gone, now electron volt is coming up, and what was the electron volt gain? And then that can be converted into joule. 1 electron volt was a 1.6 10 to the minus 9 joule. Okay, 19 joule. It was a 19. Yeah, it was a 19 joule. Okay, so then this is gone, and then what's the surviving term? The joule. Okay, and then if you essentially just multiplied all this 0.9245 931.5 to the 10 to the 6, 1.6 to the 10 to the minus 19, there will be a joule. Okay, so if you do that, and you will get this number. Okay, so that's the number that you will get by solving this problem. Okay, so this is the end of it for the exam on the nuclear chemistry. Okay, and let me